chapter 9, which was really about stoichiometry, and last time we talked about really basic stoichiometry type problems. And remember that in a basic sort of stoichiometry problem, there's really kind of 4 steps that you want to follow. You want to balance the equation, and that is a really important step. Pretty much all your calculation will be incorrect if you're not with a balanced equation. So you want to make sure you always do start with that. Even if it's given to you, you want to make sure you take a look at it, make sure that it is balanced. Also, as we talked about, if you're given everything in words, you want to first start out with the correct formulas and then balance the equation. Once you do that in a basic stoichiometry problem, you're pretty much only given one piece of information about somebody in the equation, and whatever units that may be in, you pretty much want to convert to moles. So very commonly, the last part of that conversion or some part of that conversion before you get to moles usually involves going from grams to moles. You may have to do some type of other conversion to get to grams first, but then go to moles afterwards. Once again, that is the molar mass from the periodic table in grams per mole that we use to do that conversion. Once you have it in moles, the reason you need it in moles is really for the stoichiometry part, which, as we talked about, really is just a conversion factor. And again, we're from the balanced equation rather than, say, looking it up in a table or anything like that. So the third step really is to go to the equation and find the mole to mole relationship. And in the case of a basic stoichiometry problem, pretty much the 2 things you're interested in is whatever they gave you in terms of a value, and then obviously usually what you're trying to find. So those are usually the 2 things that you're interested in that. Once you do that, that's pretty much the stoichiometry. And remember that that's really from the balanced equation, and it's really just the coefficients in front of whatever you're interested in is really how we get that sort of mole to mole relationship. Last step is really to convert those moles to some other unit. Very commonly, we're asked for grams at the end, which means a lot of times we will use the molar mass here on the back end of the calculation to convert to grams, but it really can convert to any units that they ask you for. So it may be more than one conversion at the end. But those are really the 4 basic steps to any type of basic stoichiometry problem. You basically just start at the first one, continue on. If something's done for you, just go to the next step. Don't go backwards, and you should end up at the right question at the end or answer at the end. Any questions on any of that there? All right, so I think we were going to do this one, right? Or we so let's take a look at it and see how we again can kind of do these. In this particular problem, they gave us the molar mass of each of these compounds here, and that again is from the periodic table. And if they did not give it, which is very common, they usually don't give it to you, you would have to go to the periodic table, use the formula, and calculate the molar mass of each of those substances. So really, in this case, we want to start with our first step, which is to balance the equation, and here it actually is balanced for us, so that's good to go. The second thing is they really only gave us one piece of information, which is we are starting with 0.7752 grams of this guy, and we eventually want to figure out how many grams of our product that we're going to produce. So the second step is to convert that into moles. And we would do that in this case. So it's going to be 0.7752 grams of K2PtCl4. We will use the molar mass that was given to us. And again, if it was not given to us, I guess we should circle the right molar mass, use the right one. That would be the from the periodic table that we would get that. Remember that we want to set this up dimensional analysis way. So we want to get rid of the grams. So using the molar mass, we're going to put the grams on the bottom per mole of our K2PtCl4. And that would be our second step here. If we stop the calculation right at this point, our grams of our K2PtCl4 will cancel out, and we're left with moles. Once again, as we talked about last time, you could get an answer at this point if you wanted to. If you choose to do so, you definitely shouldn't round very much. You should take it to a few extra digits. If not, you really can just continue on with the calculation, which is what I'm going to do now. And that's going to be the third step, which is the mole to mole relationship. And again, we're going to go to the balanced equation to get that. And in this case, we're interested in this guy, which was given to us. And ultimately, though, we want to get over to that guy. And here we would use the coefficients, which in this calculation doesn't look too bad. It looks like it is a 1-to-1 relationship. So that means for every 1 mole of the K2 PtCl4 I put in there, I get 1 mole of our product out there. Remember that that's what's referred to as the stoichiometric equality. And from that, we could get really 2 conversion factors that we could use. We could have 1 mole of our K2 PtCl4 over 1 mole of our product here. Or again, we could use it in the other fashion there, 1 mole of our product over 1 mole of our reactant here. And in this case, since we are dimensional analysis, we could clearly see that our K2 PtCl4 is on top, so we want to get rid of it. So once again, remember, opposites get rid of things. So we're going to use the conversion factor here from the equation on the right, which is the big stoichiometry step here. That's going to give us our 1 mole of K2 PtCl4, gives us 1 mole of our product in this case. The moles of our reactants cancel, and that's the third step. And that really is the sort of big stoichiometry step. And again, nothing more than the actual coefficients from the equation. And again, a reminder that if there's nothing written there, it is assumed to be 1 as the coefficient in this case. At this point, if we did want our answer in moles, we would actually be done. We could do the calculation, clean it up to sig figs. But we do want actually grams in this case, which means we do need to do the 4th step, which is take our moles, in this case, to grams. And that is also going to require the molar mass to do so. And we could use the molar mass that was given to us. And again, if it was not given to us, we would have to go calculate it from the periodic table. In this case, we want the moles to cancel. So we're going to do moles of our product here over our grams that was given to us, 300.1 grams PT. The moles will cancel, and that is our 4th step, converting those guys to the units we're looking for. Once again, we're going to multiply across the top there and divide by the bottom. So we're going to take 0.7752 times 300.1, basically, divided by 415.1, going to get us 0.5604 grams of our PtNH3 2Cl2. Sig fig wise, based really off of that first number there, as everything else probably considered an exact number. And once again, this is a product, and whenever you calculate how much product that you would produce based off the equation and the starting material or amount, that is also sometimes referred to as the theoretical yield. Any questions on any of those steps there? So really, it is just those 4 steps in a row, and should lead you to the right answer. Again, set it up dimensional analysis so you can see all the units canceling, and make sure that you're multiplying when you need to multiply and you're dividing when you need to divide. Any questions on any of those steps there? So once again, this is a basic stoichiometry problem. And again, it's basic because you're pretty much only given 1 piece of information about somebody in the equation. So what we're going to talk about next is where it gets a little bit more complicated, in the sense that you're not just given 1 piece of information, but you're given maybe multiple pieces of information. And that brings into play what is referred to as limiting reagents. They're also sometimes called limiting reactants, kind of the same thing. But basically the idea here is when you have a chemical reaction, usually everybody doesn't react perfectly equal with each other. So there's always something that sort of gets used up first in a reaction. So for example, if I was taking A plus B and I want to make A and B, there is one reagent, for example, that is what is referred to as the limiting reagent or reactant. And the limiting reagent is the one that gets used up first. In the reaction. So just for example here, I'm going to make A in my example, the limiting reagent. There's also what is referred to as the excess reagent. And the excess reagent is one that you have plenty of and actually still have some left over after the reaction. So your limiting reagent gets used up, your excess reagent you got plenty of, you even have some left over when the reaction is complete. So this occurs when you are pretty much given more than one piece of information and definitely some information about the reactants. And why limiting reagents and excess reagents are sort of important. It's really the limiting reagent that is the most important. And that is because, for example, in this basic reaction, will I be able to make any more product once I use up my A in this case? I will not be able to, guys. Quiet, yeah, thanks. So I will not be able to use up any, I will not be able to make any more product in this case if I use up all my A, right? Because I obviously need A and B to come together to make the product. So once we sort of use up the A in this case, no more product will be made. So the limiting reagent is really the most important here because it will determine how much product we can make. Because as soon as it gets used up, there is like no possibility at all that we can make any more product in this case. You know, maybe you bought hot dogs before and like hot dog buns, right? They sell you like 10 hot dogs, I think, and like 8 buns, right? So at some point you're going to run out of buns, right? Before you run out of hot dogs, before you can put them together. So that's going to be sort of a limiting reagent type situation. So when we do these type of problems and we have a limiting reagent situation basically occurring, we do have to do an additional sort of step when we're doing these stoichiometry problems to really figure out which one is the limiting reagent. So the good news is we can kind of do the same approach as we did in a basic stoichiometry problem. It will require sort of an extra step to figure out which one is the limiting reagent. And then you can kind of finish up the calculation. As we'll talk about, there's actually several different ways you can do these type of problems. So when we do have that limiting reagent or again, that limiting reactant, we always need to sort of figure out which one is the limiting reagent because that is the one we want to use when we do our calculation to figure out how much product that we make. So how do we know that it is a limiting reagent sort of situation? The way we know it is a limiting reagent situation is you're given enough information to get to moles of each reactant. So that is the big hint of, all right, they gave me a couple of pieces of information about the reactants. And although they may not be in moles, what they gave me, I could easily get to moles of each of those things. So that is how you know that is a limiting reagent sort of situation. You at some point need to calculate the limiting reagent or figure out the limiting reagent to do this problem correctly. So if you look back on sort of the examples we did up until this point, like I said before, we pretty much were only given one piece of information about a reactant. So we didn't have enough information to get to moles of each of them, but that is definitely how you can identify it as a problem. that it is a limiting reagent problem, because they will not in lights blink at you and say, hey, this is a limiting reagent problem. They'll just give you the information. So that's what you want to sort of look at when you look at the problem. As I mentioned before, we also have an excess reagent, which again, you will have plenty of that left over when the reaction is done. So these are very common sort of questions that we're oftentimes asked in limiting reagent problems. We're oftentimes asked how much product we would produce based on the limiting reagent. We're also sometimes asked how much of that excess reagent we actually still have left over at the end of the reaction. So we're going to talk about sort of how we could calculate all those things as we go through it. So just a basic example here, if we were going to make some workout buddies and we need a guy and a girl, we can see we need one of each. So obviously a guy and a girl, a guy and a girl, guy and a girl. And at that point, we are done with these guys, which means our guys in our case here would be our limiting reagent, and our girl workout people over here will be our excess reagent. And obviously, once we lose sort of our reactant there on the right, we can't make any more product. As I mentioned before, a very common question is how much of your excess is left over. So in this very simple sample, we could see that we would have 2 people left over, and that would be how much of our excess reagent in this case. And again, that's very common sort of questions. So let's talk about how we can actually calculate which is the limiting reagent, which one's the excess reagent. So as I mentioned earlier, there's at least 3 or so ways that you can do these type of problems. So I'm going to show you one way to do it, and maybe I'll just talk about the other method. And again, you can kind of choose whichever way you want to do it. So one method here is, if we look at this equation, we have our equation up on top. And in this case, we're going to assume that we are starting with 4 moles of sulfur, and we're going to mix it with 20 moles of fluorine in this case. So these are really our starting amounts. And obviously, to get to those moles, we would do what we did previously. We would take the grams if we're given grams, use the molar mass, convert the moles to get to those things. So the first steps of these problems, even if it's a limiting reagent problem, is still going to be the same. You want to balance the equation. And by the way, it is balanced here. I can recognize once again that this is a limiting reagent sort of situation because they gave me the moles of each of our reactants. So clearly I can get to the moles of each reactant. A big hint, definitely a limiting reagent problem. So once it is determined as a limiting reagent problem, we know we have to figure it out, but we still want to do our same couple steps to start with. We want to convert to moles. Once again, in this case, was already done for us. So we do not want to undo it or anything like that. So at this point in this method of figuring out a limiting reagent problem, after you convert to moles, here's where you have to do a little calculation to figure out which one is the limiting reagent. So right about here in your 4-step process, if it is a limiting reagent problem, you need to figure out which one is our limiting reagent. And the way that we're going to do it in this method is we're frankly just going to do a very simple calculation, a very simple stoichiometry calculation between the 2 reactants. And basically what we want to find out is, if I want to use up all of one of my reactants, how much of the other one would I need to do that? So I'm going to pick either one. It doesn't really matter. So I'm going to start with sulfur. So if I want to use up all of the sulfur that I started with, how much fluorine would I need? And I'm going to do this in moles. So I'm going to do this calculation in moles, which are already in moles. So I'm just going to do just a little calculation here. So I'm going to start with the moles of sulfur, which in this case is 4. I'm going to use the stoichiometry from the equation here to see that for every 1 mole of sulfur, I have 3 moles of fluorine. So this calculation is going to allow me to figure out how much fluorine I need to put in there to use up all that sulfur. Just like a normal stoichiometry problem, we're going to go opposites. So 1 mole of sulfur on the bottom, 3 moles of fluorine up on top. The moles of sulfur cancel, and I would end up with 12 moles of fluorine. That is how many moles of fluorine that I need. And that's how many moles of fluorine I need to use up all of my sulfur. First off, any question on the very small calculation there? All right, so what do I do with that number? I just figured out if I wanted to use up all of my sulfur, I would need to toss in there 12 moles of fluorine. How many moles of fluorine did I start with? 20. So I want to compare those two numbers. Do I have enough fluorine? I only need 12 and I have 20, so I have enough. And what that means is if I have enough, that means that my fluorine in this case will be my excess reagent, as I have plenty of it. And by default, the sulfur will be my limiting reagent. So by just picking one of the reactants and doing this very quick sort of calculation, we can very quickly determine which one is the limiting reagent and which one is the excess reagent. Any questions on that? Now, does it matter which reagent you choose? It doesn't, and you do not have to do both of these calculations, but just to show you that if you chose the other reagent, it will come out in terms of the same sort of result. So for example, if you wanted to use up all of your fluorine, how much sulfur is needed? So we would do a similar calculation. We would start with our moles of fluorine, which is 20 moles in this example. We would use our same relationship from the equation. So the opposite in this case, 3 moles of fluorine on the bottom, sulfur up on top. The moles of fluorine will cancel. That's going to give us 20 divided by 3. We're going to get 6.67 moles of sulfur is needed. So this number represents how many moles of sulfur I would need to use up all of the fluorine. So if I chose that instead of the first calculation, I would then compare to the moles of sulfur in this case. And do I have enough? I need 6.6, and I started with only 4, right? Do I have enough? I do not. So in this case, I don't have enough, which tells me the exact same thing. The sulfur in this case is our limiting reagent, and the fluorine is our excess reagent. So it doesn't matter which one you choose. You don't have to do them both. You could just do one calculation, and it will tell you which one's limiting or which one's the excess. And again, like I said, you don't need to do actually both of them. But in this case, I do not have enough. And that again tells me, as we saw, our sulfur is our limiting reagent, and our fluorine here would be our excess. So the nice thing about it is if you can identify at least one of the reactants as either being the excess reagent or the limiting reagent, the other one is the opposite by default. So all you have to do is basically identify one of those reactants. Any questions on how you determine which one's the limiting reagent? So why this is important is it is always the limiting reagent that determines how much product we make. So now that we did this step to determine which one's the limiting reagent, we could just pick up our normal stoichiometry here and do our mole to mole relationship with our product. And in this case, we would want to use our limiting reagent and how many moles of our limiting reagent we started with. So we would want to go back to our starting amount of our limiting reagent. We now can do our mole to mole relationship between our limiting reagent and our product, which in this case is a 1-to-1 relationship. And now we can figure out how much product we would make. 1 mole of our SF6 gives us 1 mole of sulfur. The moles of sulfur cancel, which means we will make 4 moles of SF6. This would be our theoretical yield in moles, right? And if I wanted grams, I would go to the periodic table, right? Get the molar mass of SF6, and I could figure out how many grams that would be, which would be like the 4th step in this case. First off, any questions on that there? And again, obviously, if we wanted to finish, we will do a different example. But if we want to finish, we could get to grams of SF6 by using the molar mass at this point from the periodic table. Now, in addition to allowing us to figure out which one's the limiting reagent, it's really important that you do go back to your starting amount of moles, right, of your limiting reagent and not use the one you use for your calculation. The other benefit of these calculations that we did here in the middle to figure out which one's the limiting reagent is it will also allow you to figure out how much of the excess reagents left over. So we can use these calculations to figure out how much of the excess reagents left over. So for example, here, you just find some room here. And we'll do it over here. Right there is good. So let's say we also wanted to figure out in this case how much of our excess reagents left over. So we already know that F2 is our excess reagent. And we already know from this calculation that we needed 12 moles of it to use up our limiting reagent, right? So to figure out how much of our excess is left over, we would take our starting moles of F2, which is our excess reagent, which was 20 moles. And we know we need to use 12 moles of it to use up our limiting reagent, which means when this reaction is over, we should have 8 moles of F2 left over, which once again, if we want to know how many grams that is, we could use the molar mass and figure out how many grams of the F2 would be left over. And again, that's sort of a benefit of you doing limiting reagents with this type of calculation in the middle is it allows you to sort of figure out how much excess reagent if you sort of choose the right one. So if I happen to have done this to do my excess limiting reagent calculation, I would be all set up to figure out how much of my excess is left over. If I chose the bottom one, I would then have to go back and actually do that calculation to figure out how much of the excess is left over. So a lot of cases you'll luck out by choosing sort of the right one maybe to do that calculation with, but otherwise you do have to come back. Any questions on any of those steps there? All right, so let's take a look at another one here, maybe with some real numbers, and we'll kind of go through it here. That's what we just did there. So I'll just show that there. All right, so let's take a look at this one here. So why don't you start it here and see what you come up with. So try those steps and see what you do. So we want to balance the equation. We want to convert to moles. And obviously, if it's a limiting reagent, we want to do it there. We want to then do our mole to mole. And then we want to convert from moles to some other unit. Actually, let's take a look at it together here and kind of go through this one, I think. So some numbers we're going to need is nitrogen is 1401. Hydrogen is 1.008. And I think that's all we need. All right, so first off, we have 15 grams of nitrogen gas is mixed with 85.5 grams of hydrogen gas. What is the grams of ammonia that is formed? So the first thing we want to do in any stoichiometry problem, which clearly this is we want the balanced equation. So nitrogen gas is N2, yeah. Remember, it's a diatomic. And we're going to react it with hydrogen gas, which is also diatomic, right? Which is H2 in this case. And ammonia is NH3, right? No charge. NH4 plus is ammonium, all right? So different. So we got that. So we have our equations. Remember that in this case, we were given everything in words. So I'm not going to worry about the balancing. I want to make sure, again, I get the correct formulas down, which I do have here. Now I should worry about the balancing. Is it balanced in this case? This is not balanced, right? So perhaps a 2 right about there and maybe a 3 right about there will balance us up at that point. All right, so we do have the balanced equation. In this particular case, we are given 15.5 grams of nitrogen is reacting with 85.5 grams of H2. I am given the grams of both reactants, which means I clearly could get to the moles of both reactants. And that means that this type of problem is a limiting reagent problem. Again, I could get to the moles of both reactants. So that is how you know that you have to figure out the limiting reagent at some point. You have some piece of information given to you to get to moles of each reactant. So I do know how to do a limiting reagent, but again, I'm just going to start with our second basic step, which pretty much no matter what method you choose, the first 2 steps are pretty much always the same. We're going to convert what they gave us into moles. So in this case, we have nitrogen here, which is going to give us 2 times our 1401. And that'll give us our 2802 grams per mole. We also have our hydrogen, which is 2 times 1.008 grams per mole, which will give us our 2.016 grams per mole. All right, so the first thing we want to do is we're going to take our 15.5 grams of nitrogen. We're going to use the molar mass to convert it into moles, and that will give us our 28.02 grams per mole of nitrogen. The grams will cancel, going to give us 15.5 divided by 2802. Going to give us 0.553 moles of nitrogen. I'm going to do a similar calculation for my hydrogen. So I'm going to take my 85.5 grams of hydrogen. I'm going to use the molar mass of hydrogen. I'm going to put the grams on the bottom, which is opposite, so they cancel. Grams are going to cancel here, and we got 85.5 divided by 2.016. Going to get us 42.4 moles of H2. Any questions on that? So this is really our second step, right? And again, we want to remember that what we just calculated is basically just converting the units to moles. And these are our starting amounts, right, of each of these things. Now, because it is a limiting reagent problem and we identified it as a limiting reagent problem, we need to do that little calculation to figure out which one is the limiting reagent. So that is what we're going to do next. We're going to do our limiting reagent calculation. So in this case, I'm going to pick the nitrogen. So what I want to know is if I want to use up all the nitrogen, how many moles of hydrogen do I need? And again, this little calculation between the 2 reactants is going to allow us to figure out the limiting reagent. So I'm going to take the moles of nitrogen that I just calculated, which is right here. We're going to take 0.553 moles of nitrogen. I'm going to go to our balanced equation, and from our balanced equation, it is 1 mole of nitrogen gives us 3 moles of hydrogen. And that again is our mole to mole relationship between these things. That is what we're going to use as a conversion factor. So again, we want to get rid of the nitrogen. So nitrogen is going to go on the bottom, which is 1 mole of nitrogen. Up on top is going to go 3 moles of hydrogen. So we're going to take 0.553 times 3. Going to give us 1.66 moles of hydrogen is needed. questions on that there? Now I want to compare. So this is how many moles of hydrogen is needed. This is how many moles of hydrogen I started with, right? So I want to compare those two. Do I have enough in this case? I do. I have enough. And because I have enough, that means that the hydrogen in this case is going to be my excess reagent, and it's actually going to be the nitrogen that will be my limiting reagent in this case. Any questions on that calculation to figure out the limiting reagent? All right, now that I know which one's my limiting reagent, I can pick back up with my normal stoichiometry steps. And now I'm going to figure out always from the limiting reagent to the product. So you always, again, want to go from the limiting reagent to the product, as that's the one that determines how much product that you will make. So we will finish up the calculation here. Once again, we're going to go back and use our starting amount of nitrogen, which is our limiting reagent in this case. And that, again, was our excess. So we're going to go 0.553 moles of nitrogen. I am now interested in our limiting reagent and our product in this case. And from the equation, that is 1 mole of nitrogen gives you 2 moles of our product. So we're going to use that as really like our third step in our stoichiometry problem. We have our 1 mole of nitrogen and our 2 moles of NH3. The moles of nitrogen will cancel at this point. And if I wanted the answer in moles, I would be done, right? I could just get an answer here, clean it up to the right number of sig figs. But in this case, I am looking for how many grams, which means I do have to do step number 4, which is to convert our moles of our product into grams. And I need the molar mass in this case of NH3. And that would be 1401 for our nitrogen, plus 3 times our hydrogen's molar mass. And that's going to give us some 17 and change there. 1703 grams per mole. So that's going to be our last step here, continuing on with our calculation. Moles of NH3 are on top, so we want the moles of NH3 on the bottom, which is like our 4th step that we do. 1703 grams of NH3. That is going to cancel out the moles of NH3. So we're going to take basically 0.553. We're going to times it by 2 and times it by 1703. Which means we will end up with something like 18.8 grams of NH3. That is a product, and based on the equation, that is our theoretical yield. Any question on those steps? Still really the same 4 steps. Balance the equation, convert to moles, mole to mole relationship, convert mole to something else, with an additional step of figuring out which one's the limiting reagent. Any questions on that? Now, if I wanted to figure out how much of my excess reagent is left over, I could do that in this case because I know that I only needed to use about 1.66 moles of my excess reagent. I have about 42.4 moles of it here. So our excess reagent left over would be 42.4 moles minus how much I needed. And that means that I would have 42.4 minus 1.66, about 40.7 moles of my H2 left over. And obviously, again, if I want to know how many grams that would be, I can multiply it by the 2.016, and that would tell me how many grams of it would be left over, which if I did that, 2.016, I have about 82 grams left over. So if we times that by 2.016 grams per mole, got about 82.1 grams of it left over. We only used about 3 grams of it in this particular reaction. Yeah. Any question on any of those steps there? So this is, again, one approach to do limiting reagent problems. To tell you sort of the other approach, which is a very commonly taught approach, is this. You just do two separate calculations. So you do one calculation following those 4 steps using, in this case, the nitrogen to figure out how many grams of the product you would produce. You then would do a second separate calculation using the amount of hydrogen you started with to figure out how many grams you produced. And whichever one produced the smallest number of grams is both your theoretical yield and your limiting reagent. So if you want to just do 2 separate stoichiometry calculations following the 4 steps that we talked about before, and you can compare how much product each one produces. Whichever one produces the smaller amount of product would be both your limiting reagent that you started with and your theoretical yield. So that's the other very common sort of approach to do these problems. Just do 2 separate calculations, one of which you'll just basically throw away because you don't need it, and one will tell you obviously the actual answer. So if you want to do that, which is a very commonly taught approach, you could do that. I really don't care. It's fine. I just remember that when you do that, there's only one answer at the end. Sometimes people circle both and go, that's both of the answers, because they did 2 separate calculations. So that is the alternative approach. Again, in this case, you would, in this example, take the grams of H2 to the moles of H2 to the moles of H2. And then you use stoichiometry to go to moles of our product to grams of our product. And then you would do a separate calculation starting with the grams of nitrogen to the moles of nitrogen to the moles of NH3 to the grams of NH3. You would compare. Smallest is your limiting reagent and your theoretical yield. And obviously your limiting reagent would be whichever one of these produces the smallest amount of product. So that is the sort of alternative approach, if you like that better. Any questions on that approach? We won't go over all the 30,000 that you could do this problem, but those are 2 very common ways that you could kind of do these type of problems. Any questions on that there? Okay, so let's take a look at another one here then. All right, so why don't you do this one here? You got 6.83 grams of iron allowed to mix with 9.34 grams of sulfur. Which is the limiting reagent, and what is the grams of FeS that you would form in this case? Iron is 5585. Sulfur is 3207. All right, let's take a few minutes, follow those steps. Clearly it asked about the limiting reagent, so it is a limiting reagent problem. So make sure you figure out whichever method. Okay, so let's take a look, and a couple of things here. Obviously, all problems will not say, which one's the limiting reagent and stuff like that. Once again, we can identify that this is a limiting reagent problem because they gave me 6.83 grams of iron, which means I definitely could get that into moles. And they gave me 9.34 grams of sulfur, which means I could get that into moles. And that is the both reactants in this case, and you could get them to moles based on what they gave you. So that is definitely how you know at some point you need to figure out the limiting reagent. So if we were going to do this problem here, I think I'll do it over here. So we have our Fe plus our S, making our FeS. And in this case, we are starting with 6.84 grams of this guy, 9.34 grams of this guy, and we really want to know how many grams of our product that we're going to produce in this case. So first things first, we want to balance the equation, which it is already balanced, so that's not too bad. Next thing, pretty much no matter what method you choose, you want to convert to moles, so we're going to do that. So using our molar mass from the periodic table here for iron, which is our 5585 grams per mole. That will give us for iron 0.122. I'm going to take it to an extra digit here, 3 moles of iron. And we're going to do the same thing for our sulfur, 9.34 grams of sulfur. Going to use the molar mass, which is our 3207 grams per mole of sulfur. And that's going to give us 0.2912 moles of sulfur. So once again, this is pretty much our starting amount of each of these guys. And because now that we know it is a limiting reagent problem, I'm going to use the method I just showed you. So I'm going to do that little calculation to figure out again, if I want to use up all of one of my reactants, how much of the other one I would need to toss in there with it. So in this case, I'm going to choose iron, and I want to use up all of my iron. How much sulfur is needed? So that's going to take the moles of our iron, which is 0.1223 moles of iron. We're going to find the stoichiometry between iron and sulfur. And from the equation, it's a pretty straightforward one. 1 mole of iron. We'll need 1 mole of sulfur, which again is the coefficients in our balanced equation in this case. So 1 mole of iron for 1 mole of sulfur. Moles of iron cancel. I think I could do this here. 0.1223 moles of sulfur is needed. Once again, any question on that calculation there? Now that I did this calculation, I want to compare how many moles of sulfur I need to how many moles of sulfur I'm starting with. So I'm going to take this number and compare it to my starting amount of sulfur. And in this case, do I have enough sulfur? I do. I only need 0.12 moles of it. I have 0.29. So I do have enough. So once again, once you figure out, for example, in this case, we do have enough of sulfur, that tells us that it is the sulfur that's going to be our excess reagent, as you have plenty of it. And by default, that would mean in this case that the iron should be our limiting reagent. So again, any questions on that selection? The purpose of that is that determines how much product we're going to produce, which is what we're looking to do. So now that I identified my limiting reagent, I could really pick up with my calculation. And again, here, I do want to start with the starting amount of my limiting reagent, which is that number right there. So we're going to take our starting amount of our limiting reagent. All right. We're now going to find a relationship between our limiting reagent and our product, which also looks like it is a 1-to-1 relationship. So that's not too bad. 1 mole of iron gives us 1 mole of our product. So that will be really like our third step in our stoichiometry calculation. We're going to go opposite. So a mole of iron on the bottom, a mole of our, that is FeS, which is what? Iron 2 sulfide, yes. All right, well, hopefully we know that in about an hour or so, yes. So that is going to do the stoichiometry part here, which cancels out our moles of iron. And once again, if I did want it, the answer in moles, I pretty much would be done. I could get an answer right in full yield in moles. But here we do want grams. So we do have to do that additional step of converting our moles to grams. We do have to remember, once again, at this point, we are in moles of the iron 2 sulfide, which means I need the molar mass of FeS. So that is 5585 for our iron, plus our 3207 for our sulfur. I'll borrow the line there. That's going to give us 5585 plus 3207, about 8792 looks like grams per mole. So we're going to use that as our final step here in our conversion. We want the moles on the bottom so they cancel. We want the 8792 grams up on top. So we end up with grams. So we're going to take our 0.1223, we're going to times it by 8792, and basically that's it. I'm not going to divide by anything. And that's going to get us 10.8 grams of iron 2 sulfide. That would be our theoretical yield. Once again, it is our first step, balance equation. Second step, convert to moles, figure out the limiting reagent. Third step, fourth step, basically just like a basic stoichiometry problem with the additional component of figuring out the limiting reagent. Any questions on any of those steps there? Now, the second part, I think on a couple slides down the road there is, again, here we can figure out how much of our excess reagent is left over. So if we wanted to figure out how much of our excess is left over, we could do that. And in this case, we actually chose correctly, right? Because we actually have how much of the excess reagent we need. Again, if you happen to have chose the other reagent and that wasn't the excess reagent, then you would have to actually go back and do this calculation here that we did earlier to figure out how much of that excess reagent you would need. So sometimes, a lot of times you get lucky and kind of choose the right one, but sometimes you may actually choose the one that's the limiting reagent. So if you had to figure out the excess, you would have to go back and kind of do the same calculation for the opposite one. But in this case, we know that we started with 0.2912 moles of sulfur, which is our excess reagent. We know from our calculation that we would need 0.1223 moles of sulfur to use up our limiting reagent. That means 0.2912 minus 0.1223. That means we got something like 0.1689 moles of sulfur left over, which if we use the molar mass of sulfur, which we have above, 3207 grams per mole, the moles will cancel. And this would tell us that at the end of this reaction here, we have about 5.42 grams of sulfur left over. Again, we started with about 9 grams or so of sulfur. So in this reaction, we use 3-4 grams of sulfur to do this reaction. Any questions on that added component, which is, again, a very common question sometimes asked, is how much of that excess reagent is left over? Any questions on any of those steps? Okay, so why don't you try one more here, wherever it is. All right, let's try this one here. They gave you the molar mass, so that's good. So you're gonna mix 622.7 grams of ammonia, molar mass from the periodic table right there. So you don't have to look it up. Molar mass from the periodic table of CO2, should be a small 2 on the bottom. Which of the two is the limiting reagent and how much of your product you would form. And again, this is the molar mass of your product from the periodic table. All right, so see what you come up with here. Again, a couple of things that you want to look at, because once again, they're not going to always tell you it's a limiting reagent problem. But when we look at it, we do have grams of NH3, which clearly I could get to moles. And we have grams of the CO2, which also means I could get to moles of it. So once again, I do have starting amounts of each of our reactants, regardless of whatever units they're in. I could get those guys into moles. And again, that's how you know that this is a limiting reagent problem and you need to figure out the limiting reagent. So we're going to start like normal here. We're going to balance the equation, which it looks balanced, which is good. We're going to convert what they gave us into moles. So I'm just going to do it on the next page so I have a little bit more room. So we're going to take our 622.7 grams of NH3. We're going to use the molar mass from the periodic table, which was given to us actually in this problem, which is 1703 grams per mole of NH3. That's going to get me something like 36.56 49. Once again, I'm going to take it to a few extra digits here because I know I'm obviously not done with my calculation. I'm going to do the same thing here with my 1241 grams of CO2. And I'm going to use the molar mass from the periodic table, but once again, they gave it to us here, which was nice. So we'll do that. And that's going to get me 28.19. We'll go 81 moles of CO2. Once again, taking it to a couple extra digits. This is our starting amount. And again, it is a limiting reagent problem. So just so we're clear, it is not always the smallest number of grams. Yeah. So sometimes people just always think the smallest number of grams, or smallest number of moles is your limiting reagent. It is not. So it just happens to be in a lot of examples. It turns out that way. You do have to do the calculation to figure it out, because based on the stoichiometry of the balanced equation, it may not always be the smallest number. So sometimes people get into that bad habit of, oh, this is the smallest one of what I'm starting with. That's going to be my limiting reagent. So just so we're clear, if it is a limiting reagent problem, you have to do the calculation to figure it out, and it won't always be the smallest one that's there. So with that being said, we do need to figure out our limiting reagent. So once again, we're going to do a simple calculation between one of our reactants and the other one. So I've been choosing the first guy all the time. So this time I'm going to choose the second guy. So in this case, I want to use up all of my CO2. How much NH3 is needed? So I'm going to start with my moles of CO2 that I started with here. I'm going to go to the equation and find the relationship between those two guys. And from the equation there, we see for every 2 moles of NH3, we have 1 mole of CO2. So that's going to allow us to have that relationship between the two. We're going to put the moles of CO2 on the bottom and the moles of the NH3 up on top. The moles will cancel. So we're going to take our 28.1981 times it by 2. That means we need about 56.3962 moles of NH3 is needed to use up all of the CO2. So once again, we do want to compare. We're going to compare that to our starting amount here of NH3. Do I have enough in this case? I do not have enough, right? I need 56. I only got 36. I do not have enough. So because I do not have enough, that tells me that it is the NH3 that is our limiting reagent. And by default, the CO2 is our excess reagent. Any question on that part? So again, you could choose either one. They both will tell you the same thing in terms of which one's the limiting reagent, which one's the excess reagent. Now that we have made our determination that the NH3 is the limiting reagent, we always want to use the starting amount of our limiting reagent, which we already have in moles. And we're going to now do from our limiting reagent to our product, which is what we're trying to find here. And from the equation, it is 2 moles of NH3 gives us 1 mole of our product. So we're going to use that as a conversion, figure out how much product we're going to produce. So 2 moles of NH3 on the bottom, our 1 mole of our product up on top. If we stop right there, once again, we will be in moles of our product, which if we wanted it in moles, we would be done with the calculation. That would also, again, be your theoretical yield of your product. But again, here we are looking for grams. So we do need the molar mass, and they were nice enough to give it to us in this problem, and that was 6006. Once again, if they didn't give it to you, you have to go to the periodic table and calculate it yourself. So we're going to use what they gave us, which was 6006 grams per mole of our product here. And that would get us 36.5649 times 6006 divided by 2 gets us about 1098 grams of our product here. And we do want to kind of clean it up. So since really the numbers they gave us was about 4 significant figures there, that actually looks cleaned up enough, actually. So that will work. 1098 grams, which would be our theoretical yield in grams. Any questions on those steps? Now, to finish up the second part of the question, which was how much of the excess reagent we would have left over. In this case, we did not choose good for that question, right? We actually chose the limiting reagent. So this is what I was saying before. If you happen to have chose the limiting reagent when you did that, all you have to do now is go back and do the opposite reactants and do the same calculations. So I'm going to do a calculation now to figure out how much of that excess reagent I need. So I want to know if I want to use up my limiting, which is the NH3, how much CO2 is needed. So we'll start with our NH3, which is 36,5649 moles of NH3. We'll use our same relationship that we used earlier, just reversed. So our 2 moles of NH3 to our 1 mole of CO2. Moles will cancel. That tells us that we would need about 10.282 moles of CO2 is needed. Now that I have that number, which is how much of the excess reagent I need, I could take the moles of my excess reagent that I started with and subtract the 2. So 28.1981 moles of CO2 started with. Subtract it to 20, I'm sorry, that's 18, I think, huh? I got the, looked like a 0. Sorry, 18, there we go. So 28.1981 minus my 18. And that's going to give me that I have 9.916 moles of CO2 left over. And if I want to know how many grams that is, I could use the molar mass of CO2, which is 4401 grams per mole that we used earlier. Those will cancel. And that will get me about 436.4 grams of CO2 is left over. So even if you maybe chose the incorrect one for the excess one, you could just go back and do the other reagent, the same calculation, and you can figure out how much of that excess reagent you needed, and you can figure out how much would be left over. Any questions on